What if the most fundamental law you know is not a law at all? What if it's just a local guideline? We as a species have spent our entire existence bound to a single foundational truth. Things are made of something. Rock, water, iron, ice, solids, liquids, gases, all tethered by the reassuring pull of gravity to a central tangible core. This is our cosmic common sense, the bedrock of our understanding, etched into our minds by the worlds we know best. Our own solar system, a grand and familiar celestial neighbourhood, has been our only textbook for what a planet can and should be. It's a family album of cosmic archetypes, each one a lesson in planetary formation. There is Mars, the silent red historian. A world painted in rust and dust, its canyons are scars from a watery past, a ghostly memory of rivers that now flow only in our imagination. It is a world of substance of rock and frozen carbon dioxide, a planet you could with the right equipment stand upon and leave a footprint. It is for all its alien beauty reassuringly solid. Then we journey outward past the belt of shattered world fragments into the realm of giants where the rules of scale are rewritten. Here is Jupiter, the raging, magnificent king. A colossal sphere of hydrogen and helium so immense it bullies the orbits of its neighbours, a failed star that channels its fury into a storm larger than our entire planet. Its swirling bands of ammonia clouds and its great red spot, a perpetual hurricane, are just the visible skin of a world with pressures so intense they crush gas into a bizarre metallic liquid deep within its heart. It has no surface in the way we understand it, yet it possesses an undeniable physical heft, a gravitational anchor that commands its own miniature solar system of moons. It is a world of immense density, a testament to the power of gravity to gather and hold. Beyond it hangs the jewel of our sky Saturn, the planet that taught us about cosmic artistry, its rings a breathtaking spectacle, a shimmering disk of countless ice particles, each a tiny moon in its own right, orbiting in a cosmic ballet of impossible grace and precision. The planet itself is a gentler giant than Jupiter, a pale yellow globe of gas so light for its size that if you could find an ocean large enough it would float. But even this ethereal world is defined by its material nature, its icy rings, its hazy atmosphere, its presumed rocky core, a seed from which it grew. These are not phantoms, they are places. And as we venture further into the cold blue twilight of the outer system, we find the ice giants Uranus and Neptune. They are worlds of exquisite mystery sapphire and aquamarine sentinels in the deep dark. Neptune whipped by the fastest winds in the solar system, a place where clouds of methane ice scud across a deep blue atmosphere. Uranus, the oddball, tipped on its side, a world of extreme seasons and frigid calm. Beneath their gaseous shrouds lie bizarre, slushy mantles of water methane and ammonia ices. Compressed under such extraordinary pressure, they behave like neither solid nor liquid. And at their centres, we believe are cores of rock and metal, the original planetary embryos that started it all. Rock, ice, dense compressed gas. This is the pattern. This is the recipe for a planet as written by our own solar system. From the scorched, dense rock of Mercury to the frozen methane of Neptune's moon, Triton, every world, every moon, every object of significance we have ever studied up close has had a tangible physical nature. They are all variations on a theme, a cosmic symphony composed with a limited set of instruments. For generations, this was our entire universe of possibility. When we dreamed of worlds beyond our own, we dreamed of places like these. We searched for Earth's twin, a blue marble orbiting a distant sun-like star. We imagined rocky super-Earths with crushing gravity, or gas giants even larger than Jupiter with rings that would dwarf Saturn's. Our science fiction, our scientific hypotheses, all were extrapolations of the familiar. We were like islanders who had never left their shore, imagining other islands with different trees and strange animals, but still fundamentally island solid land in a vast sea. The idea of a world that was not an island, a world that was only the sea itself, was not just science fiction, it was a logical absurdity. A planet by its very definition was a thing, a celestial body, an object. It had to be made of something. But the universe, it turns out, has a far more radical imagination than we do. and to see its wildest creations we had to leave the safety of our celestial island and cast our gaze into the boundless ocean of the Milky Way. The hunt for exoplanets began not with a triumphant discovery, but with a whisper. A subtle, rhythmic wobble in the light of a distant star, a gravitational tug-of-war between a sun and its unseen companion. For the first time, we had proof that our solar system was not unique, that other stars had families of their own. The floodgates opened. The Kepler Space Telescope, our first great planetary census taker, stared unblinking at a single patch of sky for years, watching for the telltale dimming of starlight as a planet passed in front of its parent star. It was a method of profound simplicity and power, turning distant solar systems into flickering celestial Morse code, and the messages it sent back were staggering. Thousands of potential worlds, planets orbiting binary stars, worlds locked in strange resonant dances. Hot Jupiter's gas giants orbiting so perilously close to their stars that their atmospheres are being boiled away into space like cosmic comets. Mini Neptune's a class of planet that doesn't even exist in our own solar system. Lava worlds, where one side is perpetually molten rock from the star's unyielding heat. The cosmic textbook we were quickly learning was far thicker than we had ever anticipated. The local guidelines we had learned from our solar system were just that local. The universe was not just filled with copies of Mars or Jupiter. It was a gallery of the bizarre laboratory of cosmic extremes. Yet for all their strangeness, these discoveries were still just shadows. A dip in a light curve, a wobble in a star's position. We knew their size, we could estimate their mass, we could calculate their orbit. We could infer their nature rocky gaseous, but we couldn't truly know them. We were like detectives at a crime scene finding a silhouette but not the person who cast it. What were these worlds really made of? What secrets were hidden in their atmospheres? Did they have clouds? Weather? The chemical precursors to life? To answer these questions, we needed more than just a census taker. We needed a master interrogator. We needed a tool so powerful it could catch the faint filtered starlight that had passed through the atmosphere of a world hundreds of light years away and dissect that light beam by beam to read its chemical story. We needed to perform a celestial autopsy from across an ocean of interstellar space. The dream of such a machine felt like a fantasy. It would require a mirror larger than any ever launched into space, a mirror so vast it would need to fold like origami to fit inside a rocket. It would need to be cryogenically cooled to temperatures just a few degrees above absolute zero, so its own heat wouldn't blind it to the faint warmth of distant galaxies. It would need to operate 1,000,000 miles from Earth, far beyond the reach of any repair mission, a solitary sentinel at a gravitationally stable point in space known as L2. It was an engineering challenge of breathtaking audacity. A machine built to tolerances of mere nanometers, a single atom's width. A machine that had to unfurl a sunshield the size of a tennis court with hundreds of motors cables, and release mechanisms all working in perfect sequence in the unforgiving vacuum of space. A single failure at any point would have turned this multi-billion-dollar dream into cosmic junk. For years we held our breath. And then on a Christmas morning it ascended. The James Webb Space Telescope, our golden eye on the universe, began its journey into the deep dark. It is more than a successor to Hubble. It is a different kind of beast entirely. Where Hubble sees the universe in the same visible light our eyes do, JWST sees it in the infrared, the spectrum of heat and ancient stretched light. It is a ghost hunter designed to see the things that are normally invisible, the birth of the very first stars in the dawn of time, the shrouded cause of stellar nurseries where new planets are being born, and most critically for our story, the chemical compositions of alien atmospheres. When starlight passes through a planet's air molecules like water, methane, and carbon dioxide, absorb very specific frequencies of that light, leaving behind a unique pattern, a sort of chemical barcode. JWST's instruments are designed to read these barcodes with unprecedented precision. It is the difference between seeing the silhouette of a person and being able to read their DNA from a single strand of hair. As the first data began to stream back to Earth, the scientific community was electrified. Images of cosmic cliffs and glittering star-forming regions more detailed and beautiful than any before. Galaxies from the edge of observable time, their light having travelled for over 13 billion years. But among these grand cosmological portraits, the telescope was also tasked with looking at things much closer to home: exoplanets. One system in particular drew the attention of a team of astronomers. It was an unremarkable star not too different from our Sun with a known planet catalogued years before. The old data suggested it was a gas giant, a warm Neptune perhaps, orbiting its star in a tight rapid embrace. It was a perfect candidate for atmospheric analysis, a routine target to test the telescope's capabilities. JWST pivoted its magnificent honeycomb mirror and stared. It waited patiently for the planet to perform its transit to pass across the face of its star. For a few precious hours, a tiny fraction of the starlight was filtered through the world's atmosphere, before continuing its long journey to our solar system, finally being caught by the golden eye of Webb. The light was gathered, the data was sent back to Earth, and then confusion. The computers processed the information, searching for the expected chemical barcodes: methane, carbon dioxide, ammonia, the usual signatures of a gas giant. But they weren't there. The spectrum was clean. Almost unnervingly so. There was only one signal, one barcode appearing over and over with overwhelming strength. A signature so dominant and pure that it seemed to defy all planetary models. It was the unmistakable fingerprint of water, H2O. But this wasn't the signature of water vapor as a minor component in a larger atmosphere. It wasn't the signal of clouds floating in a sky of hydrogen and nitrogen. The data seemed to be screaming that there was nothing else there. The entire atmosphere, from its highest, most tenuous layers to the deepest parts the telescope could probe, was made of water. Just water. An immense, searingly hot, globe-spanning, all-encompassing atmosphere of pure steam. The scientists ran the models again and again. They checked for errors in the instrument, for flaws in the data pipeline. There were none. The telescope was telling them something impossible. It was showing them a world that, according to our textbook, shouldn't exist. A planet with no discernible surface. A world that may not even have a solid core to anchor it. A colossal, low-density sphere of superheated water vapor, held together by its own gravity, hanging in space like a cosmic ghost. It confronts us with a question so profound, it forces us to reconsider our place in the cosmos. What do you call a world made not of rock, not of ice, not of dense gas, but of vapor? Is it even a planet, or is it something entirely new, a transitional state between a planet and something else we don't even have a name for yet? The James Webb Space Telescope was built to show us the universe's past, but in doing so it has revealed a vision of the present that is far stranger, more wondrous, and more challenging than we ever dared to imagine. We have found a phantom world, a planet made of steam, and its discovery is just the beginning. We must now follow this ghost in the machine, and in chasing its secrets, we may just find the new laws that govern the cosmos. To truly grasp the revolution we are living through, you must first understand the darkness that came before. Not the darkness of empty space, but the darkness of our own profound ignorance. For millennia, the idea of other worlds was a philosopher's dream, a poet's fancy, a footnote in the grand, lonely story of humanity. We looked out at the celestial ocean and saw only ourselves, a solitary island of life in an incomprehensibly vast and silent void. The stars were beautiful, but they were distant, cold, and profoundly separate. They were not suns in their own right, but merely fixtures in our sky. To even suggest they were centres of their own planetary systems was heresy, a dangerous and radical thought that cost some thinkers their very lives. We were by all accounts utterly alone. That certainty that cosmic solitude which had defined the human experience since its dawn began to fracture not with a thunderous cataclysm, but with a whisper, a faint, almost imperceptible wobble. In the mid-1990s, astronomers Michel Mayor and Didier Queloz were not looking for planets. They were meticulously studying the light from a sun-like star 50 light-years away, a star named 51 Pegasi. They were charting its spectrum, the rainbow of light that holds a star's secrets, expecting to find the stately, predictable signature of a single isolated body. Instead, they found a tremor. The starlight was rhythmically shifting, stretching towards the red end of the spectrum, and then compressing towards the blue back and forth, with the precision of a celestial clock. A ghost was pulling on the star. Something massive and unseen was locked in an intimate gravitational waltz, with 51 Pegasi yanking it ever so slightly as it swung around in a furious orbit. The math was undeniable, but the conclusion was almost unthinkable. This invisible partner was a planet a world half the mass of our own Jupiter. Yet this was no Jupiter. It did not reside in the cold, distant suburbs of its solar system as our gas giants do. This world, later named Dimidium, was practically skimming the surface of its sun, completing a full year of full orbit in just over 4 Earth days. The temperature on its surface would be a blowtorch of over 1,000 degrees Celsius, hot enough to melt lead, hot enough for iron to exist as a vapour. It was a world from a fever dream, a class of planet our theories had never predicted, and in fact, had suggested was impossible. They called it a hot Jupiter, and with its discovery the floodgates of cosmic reality were thrown open. We had spent centuries building our model of how solar systems form, using our own neighbourhood as the sole blueprint. We expected rocky worlds huddled close to the fire, and gas giants reigning over the cold, dark frontiers. This discovery didn't just add a new page to the textbook, it set the entire book on fire. It was a stunning, humbling revelation. The universe, it turned out, did not care for our neat and tidy expectations. The discovery of 51 Pegasi b was the shot heard round the astronomical world. It was proof that we had not only been wrong, but that our imagination had been far too timid. The hunt was on. Using this radial velocity method, this technique of watching for stellar wobbles, astronomers began finding more of these cosmic monstrosities. A whole bestiary of hot Jupiters emerged from the data, each one a testament to a galaxy more varied and more violent than we had ever conceived. We were explorers charting a new continent, and every discovery was a new species of impossible creature. But this method, as revolutionary as it was, gave us only a shadowy outline of these new worlds. It was an indirect detection revealing a planet by the gravitational havoc it wreaked on its star. We could learn its mass, we could determine its orbit, but we couldn't truly see it. It was like trying to understand a person's appearance by observing their shadow. You know something is there, you can gauge its general size, but its features, its texture, its true nature remain completely hidden from view. The next great leap forward required a different kind of seeing. It required not just patience, but an unblinking machine-driven stare. We needed to watch for a different kind of shadow. Imagine staring at a distant lighthouse, a single brilliant point of light. Now imagine a tiny moth flying across the beam, momentarily dimming that light by an infinitesimal fraction. That is the transit method. If a planet's orbit happens to be perfectly aligned with our line of sight, it will pass directly in front of its star, casting a shadow that we can detect as a minuscule temporary dip in the star's brightness. The effect is almost immeasurably small. For an Earth-sized planet crossing a sun-like star, the dimming is equivalent to noticing a single gnat has blocked the light from a car's headlight 100 miles away. To catch such an ephemeral wink, you would need a telescope of unparalleled stability and sensitivity placed beyond the distorting veil of Earth's atmosphere. You would need a dedicated hunter. That hunter was the Kepler Space Telescope. Launched in 2009, Kepler was a 9-year mission of cosmic census-taking. It did not roam the sky. Instead, it fixed its gaze upon a single small patch of the Milky Way, a field containing over 150,000 stars, and it simply stared. For years it watched without blinking, measuring the brightness of every single one of those stars with inhuman precision, waiting for the telltale dimming of a planetary transit. And the worlds it found utterly transformed our understanding of our place in the cosmos. The data that poured down from Kepler was a revelation, a confirmation of a staggering truth. Planets are not the exception, but the rule. Our galaxy, it turns out, is teeming with them. There are more planets than there are stars. Let that sink in. For every single star you can see in the night sky, and for the hundreds of billions you cannot, there is at least one world, and likely more in orbit around it. Kepler's galactic bestiary was even stranger than what the wobble hunters had uncovered. It found worlds of boiling lava planets with 2 suns in their sky, and systems packed so tightly that their years lasted only a few hours. But among this staggering diversity, a new and entirely unexpected class of planet emerged as the most common type in the galaxy, the super-Earth. These are worlds larger than Earth but smaller than Neptune, a size of planet that fascinatingly does not exist in our own solar system. Are they rocky planets scaled up to behemoth proportions with crushing gravity and continents adrift on magma oceans? Or are they failed gas giants, miniature Neptunes with a small rocky core shrouded in a thick, dense atmosphere? The answer is we had almost no idea. Kepler could tell us a planet's size with remarkable accuracy, and combined with mass estimates from other methods we could calculate its density. But density is a blunt instrument. A world of rock and iron can have the same average density as a world of water and steam. The silhouette was getting clearer, but the face remained a mystery. This was the great tantalizing frustration of the pre-JWST era. We had gone from knowing of 0 exoplanets to cataloguing thousands. We had filled the cosmic zoo with countless new species. We had a list of names, sizes, and orbits. We had in effect a phone book for the galaxy. But we couldn't hear any of the voices. We knew these worlds were there, but what were they like? What was in their air? Did they have clouds? Did they have weather? Did they have the chemical building blocks for life? To answer those questions, we had to move beyond simply detecting a shadow. We had to analyze the light that filtered through the edge of that shadow. This is the art of transmission spectroscopy, and it is one of the most delicate and difficult measurements in all of science. Think of starlight as pure white light, a perfect blend of all colours. When a planet with an atmosphere transits its star, a tiny fraction of that starlight passes through the planet's thin atmospheric layer on its way to our telescopes. As it does, the molecules in that atmosphere, water, vapour, methane, carbon dioxide, act like a cosmic barcode. Each molecule absorbs very specific colours, very specific frequencies of light, leaving behind a unique pattern of dark lines in the star's spectrum. If we could just capture that filtered starlight and decode that barcode, we could read the chemical composition of an alien sky from light years away. It was a breathtakingly elegant concept, a way to perform interstellar chemistry on worlds we could never hope to visit, and we tried. With the Hubble Space Telescope and the Spitzer Space Telescope, pioneers in this field pushed their instruments to the absolute breaking point. They would stare at a transiting system for hours upon hours, collecting every possible photon-stacking observations to build up a signal from the impossibly faint noise. What they achieved was nothing short of heroic. They found the first tentative hints of water vapour in the atmosphere of a hot Jupiter. They detected the hazy signature of sodium and potassium, suggesting clouds of exotic high-temperature condensates. Each detection was a monumental victory, a front-page scientific breakthrough that offered a fleeting glimpse behind the curtain. But these glimpses were just that, glimpses. The data was often noisy, the signals vanishingly weak. The barcodes we were trying to read were smudged, incomplete, and fiercely debated. The problem was fundamental. These magnificent telescopes, for all their power, were not designed for this kind of work. Hubble is a master of all trades built to capture stunning images of the visible universe. But the most revealing chemical fingerprints, the clearest signs of molecules like water, methane, and carbon dioxide, are not found in visible light. They're hidden in the infrared part of the spectrum, a realm of light that is invisible to our eyes and largely blocked by our own planet's warm, glowing atmosphere. Spitzer was an infrared telescope, a true pathfinder, but it was small, and its instruments lacked the sheer resolving power needed to pick apart these subtle, atmospheric signals with any real confidence. We were trying to read a finely printed book from across a hazy room with the wrong prescription glasses. We could make out a word here and there enough to be tantalized enough to fuel our theories, but we couldn't read the sentences. We couldn't understand the story the planet was trying to tell us. Was that super-Earth, a water world completely encased in a global ocean and a steam-filled sky, or was it a dry, barren rock, its atmosphere stripped away by the harsh radiation of its star? We could not definitively say. Did the hot Jupiter have towering clouds of silicates, molten rock raining glass down through its atmosphere? The model suggested it was possible, even likely. But the evidence was maddeningly ambiguous. We were detectives at a crime scene with nothing but a single blurry footprint. We knew someone had been there, but we had no idea who they were. This limitation defined a generation of astronomy. We lived in an age of ghosts and shadows. The galaxy we now knew for certain was haunted by worlds beyond counting. We could sense their presence, we could measure their size, we could weigh them in the gravitational balance. But we could not see them. Not really. Not in the way that mattered. To cross that final frontier, to move from detection to true characterization, to turn those shadowy silhouettes into living, breathing worlds, with chemistry and weather and unique identities, we would need a new kind of eye. An eye so powerful, so sensitive, and so perfectly tuned to the infrared universe that it could capture those faint filtered whispers of starlight and finally decode their secrets. We needed a machine built for this single grand purpose. A dream that had been on the drawing boards for decades, a hope that sustained an entire field through the long years of tantalizing uncertainty. We needed a time machine to see the universe's dawn, and an atmospheric decoder to see our neighbouring worlds. We needed a golden eye in the dark. The limitations of our old eyes had become a wall at the edge of the cosmos, a barrier of distance and dust, beyond which lay only speculation. For decades we'd catalogued the shadows of distant worlds, inferring their presence from the subtle dimming of their stars, but the planets themselves remained phantoms, their true nature shrouded in the glare of their suns. We knew they were there, a silent census of countless potential heavens and hells, but to truly know them, to read the stories written in their skies, required a leap not of imagination, but of creation. A new kind of vision was needed, and so, after a quarter-century of design delay and relentless human ingenuity, we sent a titan into the void. A magnificent golden eye folded like a celestial chrysalis within the nose cone of a rocket, destined for a place of perfect balance 1,000,000 miles from Earth. This was not merely another telescope. This was the James Webb Space Telescope, a machine built to capture the faintest, oldest light in the universe, a temporal ghost from the dawn of everything. Its journey to the second Lagrange point, a unique gravitational oasis, where it could orbit the Sun in lockstep with the Earth, was a ballet of orbital mechanics, a month-long, exquisitely calculated coast into the deep cold. Far from the thermal noise and reflected light of our own world, Webb began its transformation. This was the most complex deployment in the history of space exploration, an autonomous high-stakes act of cosmic origami, performed without the possibility of a human helping hand. We could only watch, holding our collective breath, as data streamed back across the void. First, the solar arrays unfurled, drinking in the sunlight that would be its lifeblood. Then came the communications antenna, establishing a permanent link to its creators. But the true miracle, the heart of the observatory, was the unfurling of its sunshield. A shimmering 5-layered kite of Kapton film the size of a tennis court, it stretched out layer by delicate layer, each one thinner than a human hair. This shield is Webb's triumph over the tyranny of heat. While the side facing the sun would endure temperatures hot enough to boil water, the side cradling the telescope's optics would plunge into the abyssal cold, a breathtaking 50 degrees above absolute zero. This extreme cold is not an engineering indulgence, it is the fundamental requirement for Webb's quest. The telescope is designed to see the universe in infrared light, a spectrum of radiation invisible to our eyes, but which permeates the cosmos. Infrared is the light of heat. Every object with a temperature above absolute zero, from a star to a human body to the telescope itself, glows in these wavelengths. To see the faint infrared whispers of a distant exoplanet's atmosphere, Webb had to become colder than the signals it sought, silencing its own thermal noise until its instruments could hear the quietest sounds in the cosmic symphony. Once the sunshield was taut, the telescope's golden mirror began to bloom. 18 hexagonal segments of polished beryllium, an element both incredibly strong and fantastically light, unfolded from their launch configuration. Each segment, coated in a microscopically thin layer of pure gold, was chosen for its supreme ability to reflect infrared light. With the mirror fully opened, its honeycomb structure spanning an incredible 6.5 meters, it held nearly 7 times the light-gathering power of its predecessor, the Hubble. But a large mirror is useless if it is not perfect. Behind each segment, 7 tiny motors or actuators began their work. Guided by commands from Earth, They pushed and pulled, tilting and flexing each hexagon, with a precision measured in nanometers, a fraction of the width of a single wavelength of light. Over weeks they aligned the 18 separate mirrors, focusing them until they acted as one single monolithic perfect surface, ready to collect photons that had been travelling across the galaxy for decades, for centuries, for millennia. It is this unparalleled infrared sensitivity that transforms Webb from a mere telescope into a celestial chemist's toolkit. When a planet like the one that had captured the attention of Dr. Aris Thorne's team passes in front of its star, a tiny fraction of the starlight shines through its atmosphere before continuing its journey to us. Imprinted on that fleeting light is a secret code, a spectral fingerprint left by the molecules in the planet's air. Water vapor, methane, carbon dioxide. Every gas absorbs very specific wavelengths of infrared light, leaving behind a unique pattern of dark lines in the star's spectrum like missing notes in a musical scale. By capturing this light and spreading it into its constituent colours with an instrument called a spectrograph, Webb can read that code. It can perform a chemical analysis of a world light years away, determining the composition temperature, and even the weather of an alien sky. This is the science of transmission spectroscopy, and with Webb it was about to enter a golden age. For Aris and his team, this was the moment they had been working towards their entire professional lives. For years they had been haunted by a tantalizing signal from a small terrestrial planet orbiting a dim red dwarf star just 35 light-years away in the constellation Serpens. The planet designated Serpentis B had been detected by the old transit method. It was a super-Earth, larger than our world but smaller than Neptune, and it orbited its star in a perilously tight embrace, completing a full year in just under 3 Earth days. Its proximity to its star meant it was tidally locked one side, perpetually scorched in unending daylight, the other frozen in eternal night. Based on its size and mass calculated from the slight gravitational wobble it induced in its star, its density was surprisingly low. It wasn't a dense rocky world like Earth or Mars. It was something puffier. Something with a substantial atmosphere, a thick gaseous envelope that made it a prime candidate for spectroscopic analysis. Previous telescopes, even the venerable Hubble and Spitzer, had tried to get a reading, but the signal was just too faint, the atmospheric data lost in the noise. Serpentis B remained a frustrating enigma, a world defined only by its shadow and its pull. But with Webb, the possibility of a clear answer was finally within reach. Their observation proposal was one of hundreds submitted by teams from around the globe, each vying for a precious few hours of the new observatory's time. The competition was fierce, a peer-reviewed crucible, where only the most promising and well-defined scientific questions survived. Thorne's proposal, honed over years of theoretical modelling and preliminary research, argued that Serpentis B represented a critical test case for planetary formation theories. Was it a failed gas giant, a world that had its hydrogen and helium atmosphere stripped away by its aggressive star, leaving behind a denser core? Or was it something else entirely, a water world with a thick steam-filled atmosphere? Their proposal was approved. They were granted 4 transits of Serpentis B, a total of 12 hours of observation time on the most powerful scientific instrument ever built. The news rippled through the team with a mixture of elation and sheer terror. Suddenly, their years of abstract modelling were about to collide with hard, unforgiving reality. The planning phase began with a meticulous, almost obsessive intensity. Dr. Lena Petrova, the team's lead spectroscopist, spent months running simulations, creating a library of potential atmospheric models for Serpentis B. She built digital worlds on her computer, each one a different possibility for this distant planet. One model was rich in carbon dioxide and nitrogen, a kind of super Venus. Another was dominated by methane, a hazy orange world reminiscent of Saturn's moon Titan. A third, the one many privately favoured, was a world with a substantial amount of water vapour, mixed with the expected cocktail of other common cosmic gases. Each of these models produced a unique, predictable spectral fingerprint, a specific pattern of absorption lines they expected Webb to see. They were preparing a lineup of suspects ready to match the evidence from the crime scene. Their goal was not to discover something new, but to confirm which of the known possibilities was the correct one. It was a process of elimination, the patient systematic work that defines most scientific progress. They calibrated their expectations, reminding themselves that the first data from a new instrument is often messy, complicated by unforeseen instrumental signatures and systematic errors that would need to be carefully subtracted. As the first observation window approached, a quiet hum of anticipation settled over the team's operations center. They were scattered across the globe, connected by secure video links and data streams, but united by a singular focus. They watched on their screens as the command sequence was uploaded to the telescope, a stream of digital instructions traveling for 6 seconds at the speed of light across the million-mile gap. The commands instructed Webb to pivot its immense structure, its gyroscopes whirring silently in the vacuum to lock onto the faint red glimmer of Serpentis B's parent star. The telescope would not be taking a picture in the conventional sense. Instead, its near-infrared spectrograph, or NIRSpec, would be waiting. As the planet began its transit, that tiny, almost imperceptible dip in starlight would begin. For the next 3 hours, NIRSpec's intricate system of microshutters and prisms would capture the starlight not just before and during the transit, but moment by moment as the planet's atmospheric limb slid across the face of the star. It was a celestial scalpel designed to dissect the light to peel back the layers of that alien sky and reveal the chemistry within. On Earth, Aristhorn leaned back in his chair, the glow of telemetry data reflecting in his glasses. Everything was nominal. The telescope was stable, the instruments were cold, and the star was perfectly centered. There was nothing to do now but wait. For 3 hours, a river of photons would pour into Webb's detectors, each one carrying a piece of the puzzle. They would do this 3 more times over the coming weeks, observing 4 separate transits to build up their signal to stack the data until the faint atmospheric signature emerged from the statistical noise. The team's mood was one of cautious optimism. They were confident they would get a spectrum. They were confident it would be the most precise atmospheric measurement of a terrestrial-class exoplanet ever taken. The debate centered on which of Lena Petrova's models would prove to be the winner. Would they see the deep absorption troughs of carbon dioxide, the broader features of methane, or the complex jagged signature of water vapour, a sign that Serpentis B might indeed be a world defined by H2O? They ran betting pools, friendly wagers on the atmospheric composition. No one, not even in their most audacious career-defining daydreams, predicted the truth. They were astronomers working at the very edge of their field, charting the unknown, but they were still operating within the known rules of planetary science and atmospheric chemistry. Their models were built upon a solid foundation of physics on what we knew about how planets form and how atmospheres behave. They were preparing to find a world that, while strange and alien, would still make sense. They were waiting for a signal that would confirm their theories, a piece of data that would fit neatly into the grand emerging puzzle of exoplanetary science. What they could not know as they watched the data packets begin their long journey home was that they were about to receive a message from a world that broke all the rules. The photons captured by Webb's golden eye carried a spectral signature so bizarre, so completely alien to their models, that it would at first be dismissed as an error. It was a whisper from a world that, according to everything they thought they knew, simply should not exist. Undefined. And so, after the long silence, the universe began to speak. Not in a sudden clap of thunder, but in a quiet, methodical cascade of digital information. The first photons, having completed their lonely pilgrimage across dozens of light years, finally ended their journey inside the cryogenic heart of the James Webb Space Telescope. For months, we had held our collective breath, watching this golden eye unfurl in the dark, waiting for its gaze to settle upon our target. Now that gaze had returned. Down it streamed a river of encoded light pouring into the servers at the Space Telescope Science Institute. In a hushed control room a world away from the silent dance of the observatory, the vigil was ending. This was not a moment of instant pictures and breathtaking vistas. This was the birth of a puzzle. The raw data appeared on the screens not as a planet, but as an unforgiving wall of numbers, a cryptic language of stellar flux and photon counts. Each digit represented a tiny fragment of a story, a message that had been warped by distance, bent by gravity, and filtered through the very atmosphere we had journeyed so far to understand. For the teams of scientists who had dedicated years, even decades of their lives to this mission, this was everything. The air was electric, a delicate mix of profound hope and gut-wrenching anxiety. Every mind in the room was acutely aware of the stakes. A single, unforeseen calibration error, a minor miscalculation in the instrument's thermal stability, or an unexpected flare from the host star could corrupt this fragile message, rendering it meaningless. You could feel the weight of that possibility, a ghost haunting the sterile hum of the computer terminals. The first step was not one of discovery but of purification. A painstaking process began to digitally cleanse the data to perform a kind of computational alchemy. The goal was to subtract the known from the unknown. They had to first isolate and remove the overwhelming glare of the parent star, a celestial blowtorch that threatened to incinerate the subtle whisper of the planet's atmosphere. Using hyper-precise models of the star's own light, they began to peel it away from the combined signal layer by meticulous layer. It was like trying to hear a pin drop in the middle of a symphony orchestra, demanding an almost perfect understanding of every instrument's note. They filtered out the signature of interstellar dust the light had passed through on its journey. They corrected for the microscopic wobbles of the telescope itself, a gravitational gyroscope spinning through the void. What they were hunting for were the gaps, the missing pieces. The specific frequencies of light that the planet's atmosphere had consumed as the starlight passed through it. These dark bands, these absorption lines, were the chemical fingerprints left behind by the molecules floating in the alien air. This was transmission, spectroscopy, the art of reading a planet's story by the light it steals. As the first cleaned-up plots began to resolve, a palpable tension settled over the teams. The initial graphs were messy, jagged with residual noise, but within them the nascent shape of a spectrum was starting to emerge. Not just one peak, but a whole forest of them. A complex serrated landscape of light and shadow. Then one particular feature started to grow to sharpen. It was in a region of the infrared spectrum that every atmospheric scientist knows by heart, a place they fully expected to see something. But not like this. What was emerging from the noise was not a gentle hill in the data. It was a mountain, an entire mountain range. A series of deep, impossibly broad absorption troughs that were so prominent, so utterly dominant they seemed to warp the entire baseline of the spectrum. An astronomer leaning so close to her monitor that her breath fogged. The screen murmured the words almost involuntarily. That's water. Of course it was water. Water is everywhere in the cosmos. Finding its signature was predicted, even required by their models. But this was different. This signal was monstrous. It was a roar. The spectral lines for water vapour were not just present, they were so profoundly deep and wide that they suggested a colossal abundance. The initial algorithms struggling to quantify it began returning numbers that seemed like typos, percentages that flirted with the impossible. A nervous quiet descended as the scientists stared, their minds racing through every possible explanation. Could it be an artifact of flaw in the detector's sensitivity at this specific wavelength? They pulled up the calibration files, running diagnostic after diagnostic. The instrument's health was nominal. Perfect, even. The telescope was performing flawlessly, a testament to a generation of engineering. The problem wasn't in the machine. The problem was in their understanding. The true sense of unease began to creep in when they started looking for everything else. Their models, built upon our understanding of planetary formation, had predicted a rich chemical soup. They expected to find the strong, clear signature of carbon dioxide, a heavy molecule that should anchor the lower atmosphere. They searched for the telltale peaks of methane and carbon monoxide, the fundamental building blocks of more complex organic chemistry. They scanned for ammonia, for sulfur compounds, for the vast chemical family that paints the skies of the gas giants in our own solar system. There was nothing. Or more accurately, there was next to nothing. Where there should have been clear identifiable forests of absorption lines for these other gases, there was only flat line. Faint ghostly whispers so close to the noise floor that they could easily be statistical phantoms. It made no sense. An atmosphere is a mixture, a chaotic and vibrant chemical ecosystem. To find one component in such overwhelming isolation was like finding an ocean with no salt, a forest with only one type of tree. It defied the fundamental principles of atmospheric physics. The lead scientist for one of the analysis teams called for a full stop. The excitement that had filled the room just an hour before had now curdled into a tense-focused confusion. "Run it again," she commanded, her voice steady but firm. "Triple-check the stellar subtraction. Use a different model for the star's photosphere. Let's assume we got it wrong. Let's assume we're seeing a reflection from a weird cloud deck." For hours they worked with a frantic intensity, trying to break their own discovery. They were now fighting against their own data, desperately searching for a mundane explanation, for a result that felt increasingly extraordinary. They tried to make the water signal smaller by tweaking the parameters for temperature and pressure, but the data resisted. The spectral signature was too robust. It was an incontrovertible truth written in the language of light. It refused to be anything other than what it was. Meanwhile, a second team working in parallel in a different building was reaching the same terrifying conclusion. They were using an entirely different suite of software, a competing set of atmospheric models built from the ground up to avoid this very kind of groupthink. Their mission was to be the check, the balance, the skeptical voice. A message flashed up on the lead scientist's screen from their team leader. It contained no words. Just a single stark image, their independently processed spectrum. It was identical. The same colossal canyons carved out by water. The same barren plains where the signals for carbon and methane should have been. The silence in the first control room deepened. The fight was over. The data had won. This was the moment. Not a single shouted eureka, but a slow, dawning collective epiphany that rippled through the room. A quiet, profound sense of awe. People began to stand up to walk over to the main screen as if proximity would make the truth more real. They were looking at the chemical portrait of a world whose atmosphere was not just water-rich. It was for all intents and purposes water. Pure, unadulterated water. They had been searching for a planet with clouds and oceans, and instead they had found a planet that was a cloud. An entire world enshrouded in a global suffocating blanket of steam. The implications were staggering, almost vertigo-inducing. The very concept challenged the core tenets of planetary science. Such a world would have to possess a surface pressure and temperature so extreme that it would exist in a bizarre supercritical state, a fluid that is neither liquid nor gas. It would be a place of unimaginable violence and power. One of the younger postdocs staring at the final verified graph summed up the feeling that had settled over them all. "We were looking for Earth's cousin," he said, his voice barely a whisper. "Instead, we found a ghost made of steam." He was right. They had peered into the heart of a new cosmic archetype, a class of planet that until this moment had existed only in the most speculative theories. It was a world without a defined surface, a planet whose very substance was its sky. The numbers that had seemed like errors just hours ago were now being accepted as fact. The atmospheric composition was not 10, 20, or even 50% water vapor. It was upwards of 99%. An atmosphere of almost pure steam stretching for hundreds, perhaps thousands of miles, pressed down by gravity into a crushing, searing abyss. For a long time nobody spoke. They simply stared at the evidence, letting the sheer, unadulterated strangeness of their discovery wash over them. They had set out to find a world, and they had succeeded beyond their wildest imaginations, but in doing so they had shattered the very definition of what a world could be. The puzzle they had just solved, the chemical composition of this alien atmosphere, had instantly given way to a newer, far more profound mystery. The neatly plotted graph on the screen was no longer just a piece of data. It was an accusation. It was a challenge delivered across the vastness of space, aimed directly at our understanding of the cosmos. The message was clear. You think you know how planets are made. You think you understand the rules you don't. How could a planet like this possibly form? What cataclysmic history or bizarre physics could conspire to create a world stripped of nearly every other element, leaving behind only the ghost of water, and perhaps the most tantalizing question of all? If the sky itself is an endless ocean of steam, what if anything lies beneath? The signal was unequivocal, a spear of perfect data piercing the heart of every known planetary model. In laboratories and universities across the globe, the graphs that painted a portrait of this impossible world were projected onto screens checked and then checked again. A quiet disbelief fell over the community, the kind of silence that follows a magic trick cannot be real, and yet you saw it with your own eyes. The numbers from the James Webb Space Telescope were not a smudge, not an artifact, not a ghost in the machine. They were a testament written in the language of light to a planet whose sky consisted of almost nothing but water. Just steam stretching from the unseen surface to the edge of space. For the scientists who had spent their lives building a cohesive story of how worlds are born, this was like discovering a book where every single word was the same. It was grammatically correct, but it made no sense. The universe, it seemed, was not obligated to follow our narrative, and so began the great grappling. How do you form a world like this? You're looking at a fundamental violation of cosmic chemistry. Planets are not curated collections. They are messy, chaotic gatherings of what was available in their corner of the protoplanetary disk. They accrete from a swirling fog of hydrogen, helium, carbon, silicon, oxygen, and countless other elements. A planet is a history of this cosmic dustbin. Yet here was a world that appeared to have thrown everything else away, keeping only hydrogen and oxygen perfectly bound in the simple, elegant molecule of H2O. It was an act of cosmic minimalism so extreme it bordered on the absurd. The challenge was not merely to explain a strange weather pattern, but to write an entirely new planetary biography, a life story that could lead to such a bizarre monolithic endpoint. The whiteboards were wiped clean. The old assumptions which had served us so well from the rocky plains of Mars to the gas giants of the outer solar system were now just fossils of a simpler time. Two grand competing narratives began to emerge from the intellectual fray, two epic tales of planetary evolution, each one a desperate attempt to reconcile the impossible data with the fundamental laws of physics. The first of these ideas was perhaps the more poetic and certainly the more tragic. This theory imagined a world that was not always a monster of steam. It painted a picture of a planet that might have once been beautiful, a world born in a gentler orbit, swaddled in a thick atmosphere, and blessed with oceans of liquid water. Imagine it a water world larger than Earth, its surface a single globe-spanning ocean under a pale, distant star. For millions, perhaps billions of years, it could have been a place of staggering potential. But planets are not anchored in the sky. Their orbits are a slow cosmic dance, and sometimes the music changes. This first story is one of a fall from grace, through gravitational nudges from a sibling planet, or the slow, inexorable decay of its own orbit. Our ocean world began a long inward spiral. It crept closer and closer to the star it once viewed from a safe distance. The gentle warmth it had known became a relentless blistering heat. The star, once a life-giver, was transforming into a celestial blowtorch. The process would have been agonizingly slow at first. The oceans, vast and deep, would have resisted their thermal inertia, a powerful shield. But physics is patient and unforgiving. The surface temperature climbed past the boiling point of water, not just in the tropics, but everywhere from pole to pole. A planetary fever began to rage. The ocean started to boil, not just a simmer, but a violent churning evaporation on a scale that beggars belief. A thick, planet-shrouding blanket of steam would have risen, wrapping the world in a prison of its own making. This colossal greenhouse effect would have accelerated the process, trapping more and more heat, pushing the temperatures ever higher until the very distinction between ocean and atmosphere dissolved into a single terrifying entity, a supercritical fluid, a strange state of matter, neither liquid nor gas. At this point, the planet becomes a cosmic pressure cooker, a hellscape of unimaginable temperature and crushing pressure. But the true violence was happening higher up at the very edge of space. Here the star's radiation, its unfiltered fury of ultraviolet and X-rays, became a weapon. This high-energy light slammed into the water molecules that had risen to the top of the atmosphere, acting like a quantum hammer, shattering the strong bonds holding them together. Photodissociation. The scientists called it a gentle name for a brutal act of molecular destruction. Water molecules, H2O, were systematically torn apart into their constituent atoms, 2 hydrogen, 1 oxygen. And here in this high-altitude slaughter, gravity played the role of the final executioner. Hydrogen, the lightest of all elements, found it easy to escape. Kicked by the energy of the star, these individual atoms achieved escape velocity, bleeding off into space like a never-ending sigh. You must picture it a steady, silent fountain of hydrogen atoms, leaving the planet forever, a river of lost potential flowing into the void. The planet was exhaling its very essence. The heavier oxygen atoms, 16 times more massive, found it much harder to break free. They were gravitationally shackled to the wounded world. Over eons, this process known as hydrodynamic escape would fundamentally and irrevocably alter the planet's chemistry. It would strip the world of its hydrogen, leaving a surplus of lonely reactive oxygen. In most models, this leftover oxygen would either form its own thick atmosphere or aggressively oxidize the planet's rocky surface, turning it into a global desert of rust. To get the pure water vapor atmosphere we see on Ethel, something else must be happening. The modelers had to add a new crucial wrinkle. What if the planet had a vast internal reservoir of water, a mantle saturated with H2O, constantly feeding the atmosphere from below through immense volcanic processes? The world becomes a dynamic, violent machine. Water is dredged up from the interior, vaporized into the atmosphere, torn apart at the top by the star, and its hydrogen is lost to space. It is a one-way ticket to oblivion, a planet slowly consuming itself to maintain its bizarre, steam-filled sky. In this telling, Ethel is not a static object. It is the ghost of a dead ocean, a world caught in the final agonizing act of its own self-destruction. It is a monument to loss, a reminder that even the most promising worlds can be brought to ruin by the simple, unforgiving mechanics of their solar systems. The second theory was less a story of tragedy and more a story of an alien genesis. It proposed that Ethel was never a gentle ocean world. It was born a monster. This narrative begins much farther out in the protoplanetary disk, far from the star's warmth, beyond a crucial chemical boundary known as the snow line. Out here in the frigid darkness of the outer system, water is not a liquid or a gas. It is ice as common and as solid as rock. Trillions of icy planetesimals, cosmic snowballs mixed with dust and carbon, swirled in a slow, patient dance. From this frozen bounty, a planetary embryo began to grow. It swept up ice and rock with ruthless efficiency, its gravity swelling as its mass increased. It became a super-Earth, not of dry silicate rock like our own world's core, but a body composed of a vast percentage of water ice. It was a scaled-up Ganymede or Europa, a world whose very bones were made of frozen water. For a time, it may have orbited peacefully in the cold, a silent, icebound giant. But planetary systems are restless places in their youth. The immense gravity of larger, more distant planets can stir the pot, flinging smaller worlds around like stones in a catapult. Our icy super-Earth was kicked from its serene frozen orbit. It began a long, majestic and terrifying journey inward, a pilgrimage toward the furnace at the heart of its own solar system. This process, planetary migration, is now understood to be a common if violent feature of cosmic architecture. As it travelled, the world would have ploughed through the remaining debris of the disk, its trajectory, a billion-year fall toward the star. The closer it got, the more the star's radiation intensified. The ice, which had been stable for eons, began to feel the heat. The surface would have softened, then melted, then boiled. But this was not the gentle boiling of a terrestrial ocean. This was the sublimation and vaporization of a crust of ice thousands of kilometers thick. The entire planetary mantle, a colossal reservoir of H2O, began to outgas, releasing a torrent of steam that would dwarf any volcanic eruption in our own world's history. An atmosphere of pure water vapor was not something that evolved. It was the planet's primordial state unleashed as it thawed. It was never anything but a steam world. This theory is elegant in its simplicity. It doesn't require the messy multi-step process of boiling an ocean and then methodically stripping away its hydrogen. It suggests Ethel is what you get when you take a water-rich planet and simply move it. You drag it from the freezer and place it in the oven. The world we see today is the direct, unadulterated result, a planet whose atmosphere is a direct expression of its overwhelmingly water-rich composition. It is not the ghost of an ocean. It is the unveiled soul of an ice giant. To test these two competing epics, the scientific community turned to their most powerful tool for exploring the impossible, the supercomputer. Digital universes were brought into being powered by processors capable of trillions of calculations per second. In these virtual laboratories, scientists became gods, forging planets from scratch and tormenting them with simulated stars. They could build the ocean world of the first theory, giving it a precise mass, a specific orbital distance, a particular atmospheric density. Then they would begin its death march. programming the subtle gravitational nudges that would pull it inward. They watched frame by agonizing frame as the virtual star's energy output was dialed up. They saw the digital oceans boil, the atmosphere swell, and they meticulously tracked every atom of simulated hydrogen as it was blasted into the void. They ran the simulation 1,000 times, 1,000,000 times, tweaking each variable. What if the star was more active, prone to violent flares? The hydrogen escaped faster, but so did the oxygen, leaving a barren rock. What if the planet's magnetic field was stronger? It might protect the upper atmosphere, slowing the hydrogen loss to a crawl, preventing the formation of a pure steam envelope. What if the planet had a different internal composition, less water, locked in its mantle to replenish the sky? The atmosphere would vanish in a cosmic blink. They discovered that to create the ghost of an ocean, you needed a Goldilocks scenario of death. The planet had to be massive enough to hold onto its oxygen, but not so massive that it held onto its hydrogen. Its star had to be energetic enough to split water molecules, but not so violent it sandblasted the entire atmosphere away. The inward migration had to be slow enough to allow for the gradual atmospheric transformation. It was a cosmic balancing act on a knife's edge. The theory was possible, but it required a perfect storm of cosmic coincidences. Simultaneously, in other digital realms, the second theory was being put through its own crucible. Scientists would seed a virtual protoplanetary disk with a high concentration of ice beyond the snowline. They would let gravity do its work, watching as a water-rich super-Earth coalesced in the frozen depths. Then came the migration. They programmed the gravitational kicks from simulated gas giants, sending their icy creation on its inward journey. They watched as the star's heat peeled away the layers of ice, creating that primordial steam atmosphere. Here too the variables were legion. How fast did it migrate? If it moved too quickly, it might plunge directly into the star. Too slowly, and it might lose too much of its mass to the stellar wind along the way. What was its initial ice-to-rock ratio? Too much rock, and you'd get a significant contribution of other gases like carbon dioxide and sulfur dioxide from volcanism polluting the pure water vapor signal. These models, these digital ghosts of Ethel, became a battleground for ideas. Teams of astrophysicists, their allegiances informally pledged to one theory or the other, would present their findings. A group from Munich would publish a paper showing a successful run of the ghost ocean model, but only if the star had a very specific and rare period of low X-ray activity in its youth. A competing team from Caltech would counter with a breathtakingly beautiful simulation of a migrating ice world, demonstrating that it could perfectly reproduce Ethel's atmosphere, but only if its core was strangely depleted in radioactive elements, keeping internal volcanism to a minimum. Lines were being drawn in the digital sand. The debate was no longer about whether Ethel existed, but about its soul. Was it a fallen paradise or an alien prince born to a bizarre destiny? Was its story one of profound loss, or one of an entirely different kind of beginning? Both theories, as elegant and compelling as they were, seemed to lead to the same unsettling conclusion: Ethel should not be common. Both the tragic tale of the boiled ocean and the epic of the migrating ice giant required a precise and unlikely sequence of events. They were cosmic corner cases, scenarios so specific that finding even one example felt like a staggering stroke of luck. And yet the universe is vast. The number of stars and planets defies easy comprehension. Perhaps unlikely on a cosmic scale still means that there are thousands, even millions of such worlds burning in the dark. But the models had reached an impasse. They'd given us two plausible yet deeply flawed pathways to this impossible world. They showed us how it could happen, but not how it did. The faint light captured by Webb had told us what Ethel is, and the powerful simulations had given us two competing stories for why. But to uncover the truth, to choose between the ghost and the giant, we would need more than just theory. We would need to go back to the telescope. We would need to find a way to read the deeper, more subtle clues hidden in that steam-shrouded sky, and so we find ourselves standing at the edge of an intellectual abyss. The James Webb Space Telescope. Our great eye in the dark has not simply shown us a new world, it has presented us with a cosmic riddle wrapped in an enigma of steam. The data streams are unambiguous, the spectral lines as clear as a fingerprint left at the scene of a crime. We have found a planet composed almost entirely of water vapour, a world without a discernible surface, a ghost woven from the very molecule that gives us life. Yet the existence of such an object tears at the very fabric of our understanding of how planets are born and how they survive. It's a flagrant violation of the unspoken rules we thought governed the cosmos. How can a world made of something so ethereal, so prone to escape, possibly endure the violent onslaught of its parent star? How can it hold itself together against the ceaseless, unforgiving vacuum of space? The discovery itself, as we've seen, was a triumph of technology, but the explanation, that is a triumph of imagination, a battleground where theories clash in a desperate attempt to make sense of the impossible. To even begin to comprehend this phantom world, scientists have had to abandon their textbooks and venture into the wild frontiers of planetary science, armed with only computer models and the audacious power of human curiosity. Two primary and profoundly different visions have emerged from the fierce debates raging within the astronomical community. Each paints a portrait of a world so alien it strains the limits of language itself. The first of these great hypotheses asks us to imagine not a planet in the classical sense, but something far stranger, a superpuff. Picture an object with the gravitational heart of a planet, perhaps a small core of rock and exotic ices a few times the mass of Earth. But then imagine an atmosphere, a colossal envelope of water vapour that has swelled to an outrageous, almost unbelievable size. This wouldn't be a planet with a thin atmospheric skin like our own, but a world that is its atmosphere. Its density would be absurdly low, more comparable to cotton candy than to rock. It would be a cosmic dandelion seed, a vast diffuse sphere of steam whose edges blur into the vacuum of space. As you approach such a world, you wouldn't see a sharp defined limb like Earth's or Jupiter's. Instead, you would fly into a gradually thickening haze, a celestial fog bank spanning hundreds of thousands of kilometres. The transition from interplanetary space to the planet itself would be a gentle, almost imperceptible journey, the stellar backdrop slowly dimming as you sink deeper into its tenuous gaseous sea. The very concept of a surface would be meaningless here. There would only be a slow, inexorable increase in pressure and temperature as you descend toward the tiny unseen core, a journey through endless layers of vapour. The formation of such a ghostly giant presents its own tantalising puzzle. Perhaps it was born in the frigid outer reaches of its solar system, far beyond the frost line where water ice was plentiful. In that cold darkness, it could have accumulated a titanic atmosphere of vapour sublimated from ice, a primordial envelope it held onto loosely. Then, through a game of gravitational billiards with other larger planets, it was catapulted inward, embarking on a long, slow migration toward its star. As it spiralled closer to the furnace, the increasing heat would have caused its already vast atmosphere to expand even further, puffing it up like a loaf of bread in a cosmic oven. This journey would be a race against time. The planet would need to settle into a stable orbit before the star's intensifying radiation could strip its precious vapour away entirely. An alternative, more violent Genesis story suggests the superpuff could be the ravaged remnant of a much larger gas giant. Imagine a Neptune-sized world that wandered too close to its sun. The star's ferocious heat and gravitational tides would have begun to boil away its thick outer layers of hydrogen and helium, the lightest and easiest elements to lose. Over millions of years, this celestial blowtorch could have peeled the giant like an onion, leaving behind only its denser, water-rich inner mantle, now exposed and swollen under the relentless heat. In this scenario, our steam world isn't a pristine migrated body, but a battle-scarred survivor, the naked core of a world that once was. But this beautiful ethereal image of a cosmic ghost is haunted by one overwhelming question: stability. How does something so large and so flimsy possibly survive? Every moment of its existence, the superpuff is under a multi-pronged assault from its parent star. First, there is the stellar wind, a constant hurricane of charged particles blasting outward at 1,000,000 miles per hour. This cosmic sandblaster should by all rights erode such a tenuous atmosphere, carrying it away particle by particle into the interstellar medium. Then there is the more insidious threat of high-energy radiation. X-rays and extreme ultraviolet light from the star act like a scalpel, energizing the water molecules in the upper atmosphere to speeds that exceed the planet's escape velocity. This process, known as hydrodynamic escape, should be brutally efficient for a low-density world, causing its atmosphere to boil off into space like steam from a kettle. To survive this relentless siege, the superpuff would need a secret weapon. A powerful global magnetic field generated by a churning conductive core could be its saving grace. This invisible shield would deflect the worst of the stellar wind, creating a protective bubble, a magnetosphere around the fragile world. The auroras on such a planet would be a spectacle beyond our wildest dreams, shimmering curtains of light not tens but hundreds of thousands of kilometers high, a constant silent testament to the battle being waged between the planet and its star. Yet even with a magnetic shield, the sheer size of the atmosphere presents a problem. Its outer layers would extend so far that they might lie beyond the protective reach of the magnetic field, a sacrificial vanguard offered up to the stellar winds. This leads to a startling possibility. Perhaps what we are seeing is not a stable world at all, but a transient phenomenon. We might have caught this planet in a brief fleeting moment of its life, witnessing its slow, inevitable demise as its watery essence bleeds away into the void. It might be a magnificent dying ghost, and we are merely lucky witnesses to its final spectral act. Faced with the profound fragility of the superpuff model, another faction of scientists proposes a radically different and far more violent solution. What if our intuition is wrong? What if the planet isn't a diffuse ghost, but a dense, compact, and incredibly hostile inferno? This second leading hypothesis takes us from a world of celestial fog to a world of unimaginable pressure. It posits a planet that is also dominated by water, but where the conditions are so extreme that the distinction between liquid and gas completely dissolves. Welcome to the dense greenhouse model. In this scenario, the planet has a much more substantial mass, packing a tremendous amount of water into a much smaller volume. Its gravity would be crushingly strong, and because it orbits so close to its star, it is trapped in a runaway greenhouse effect that makes Venus look like a paradise. The sheer volume of water vapor in its atmosphere traps the star's heat with terrifying efficiency. Temperatures would soar not to hundreds but to thousands of degrees Celsius. At these temperatures and the corresponding immense pressures, water would be forced into a strange exotic state known as a supercritical fluid. It's a phase of matter that is neither liquid nor gas, but possesses the properties of both. It can flow like a liquid, but also expand to fill a container like a gas. On this world, there are no oceans, no clouds, no rain. In any sense we would recognize. There is only a single uniform, terrifyingly deep ocean of supercritical steam, roiling and churning under its own immense weight. To journey into this world would be to descend into a planetary-scale pressure cooker. The pressure would build relentlessly, reaching levels thousands or even tens of thousands of times greater than at the bottom of Earth's deepest ocean trenches. The light from the star would struggle to penetrate the thick, turbulent fluid, creating a murky, oppressive gloom, perhaps illuminated from below by the dull, cherry-red glow of the superheated rock and metal at the planet's core. The atmosphere wouldn't just be on the planet, it would be the planet's mantle, a single continuous fluid layer thousands of kilometers deep. Its formation story is just as dramatic as its physical state. This could be the remnant core of a gas giant that had its hydrogen and helium stripped away, but unlike the superpuff, this core was massive enough to retain its heavy water-rich layers through sheer gravitational force. Or it could have formed in situ close to its star from a protoplanetary disk unusually rich in water-bearing planetesimals. These bodies would have collided and merged their combined internal heat, and the intense stellar radiation instantly vaporizing their water content, creating the runaway greenhouse effect from the moment of its birth. The key strength of this dense greenhouse model is its inherent stability. Where the superpuff is a fragile dandelion seed, this world is a gravitational fortress. Its immense gravity provides a powerful anchor holding onto its atmosphere with an iron grip. The escape velocity would be enormous, making it incredibly difficult for the star's radiation or stellar wind to strip away the water molecules. They are simply held too tightly. This world is not passively resisting its star. It is actively fighting back with the most fundamental force in the universe, gravity. It is a titanic object locked in a brutal but stable equilibrium, a permanent fixture in its solar system. It is not dying. It is enduring. It has found a way to survive in an environment that should be utterly sterilizing by embracing the inferno and making it a fundamental part of its nature. The pressure cooker isn't a bug, it's a feature. The runaway greenhouse effect, a climate catastrophe on Earth, is the very mechanism that defines and sustains this alien world. It is a testament to the resilience of planetary processes, a demonstration that nature can find stability in conditions we would consider the definition of hell. This vision challenges our terrestrial biases, forcing us to recognize that the universe has a far broader imagination than we do. It can build worlds not just of rock and gas, but of supercritical fluid worlds that exist in a permanent state of extreme crisis, yet are in their own way perfectly stable. So we are left with two competing realities, two ghosts in the machine. On one hand, the ethereal superpuff, a vast, delicate, and possibly transient balloon of steam, a cosmic phantom drifting through space. On the other, the dense greenhouse, a compact, violent, and enduring pressure cooker, a gravitational titan shrouded in a permanent superheated tempest. How do we, from a distance of hundreds of light years, possibly distinguish between these two extraordinary possibilities? Once again, we turn to the unparalleled precision of the James Webb Space Telescope. The answer lies not just in what elements are present, but in the subtle shape of the data, specifically in the light curve of the planet's transit. As the planet passes in front of its star, it blocks a portion of the starlight. By measuring this dimming with incredible accuracy, we can learn about the planet's structure. A superpuff with its fuzzy extended atmosphere would produce a very specific signature. The starlight would begin to dim gradually long before the main body of the planet begins its transit as the light filters through its tenuous outer layers. The ingress and egress of the transit would be soft-sloped curves betraying the presence of that colossal hazy envelope. In contrast, the dense world with its much sharper gravitational boundary would produce a crisper, more defined light curve. The dimming of the starlight would be more abrupt, the beginning and end of the transit more box-like. It would be the silhouette of a world with a much harder edge. Currently, the data sits on a knife's edge. The initial observations hint at a slightly softer curve, lending some credence to the superpuff model, but the error bars are still too large to be definitive. The scientific teams are locked in a collaborative race, designing new observation strategies, searching for other similar worlds to build a larger sample size. Every new photon collected by Webb is another clue, another piece of the puzzle that could tip the scales in favour of one model over the other. This isn't just an academic debate. The answer will have profound implications for our understanding of the universe. It forces us to confront the limitations of our own planetary classification system. We have terrestrial planets, gas giants, and ice giants. Where does a world made of steam fit? Does it belong to its own entirely new class? Do we call them vapor worlds, or aqueous planets, or steam giants? This discovery shatters the neat little boxes we've constructed. It reveals that our solar system, with its orderly progression from small rocky worlds to giant gassy ones, is not a universal blueprint. It is merely one possible outcome of planetary formation, a single, perhaps even provincial example, in a galactic zoo teeming with creatures we have yet to even imagine. This planet of water vapour is a powerful, humbling reminder that the cosmos is under no obligation to conform to our expectations. Its creativity is boundless. Its capacity for generating novelty is infinite. We stand at a crossroads of knowledge, staring at the spectral signature of an impossible world. It could be a delicate transient ghost, a magnificent spectacle of a planet in its death, throws a reminder of the fragility of worlds against the power of suns. Or it could be a gravitational monster, a superheated high-pressure furnace that has found a way to thrive in hell itself, a testament to the sheer stubborn resilience of matter to organize itself into a planet. Whichever reality proves to be true, we have been changed by the question. We have learned that the universe is not only stranger than we imagine, but stranger than we can imagine. And this single, baffling world, this phantom planet of steam, now serves as a beacon, illuminating the vast unexplored territory that still lies before us. The search is now on not just to solve the mystery of this one particular world, but to find its brethren. Are these steam-shrouded phantoms a common quirk of galactic evolution, or are we staring at a one-of-a-kind cosmic monster, a beautiful freak of nature? And with every new system that Webb brings into focus, we hold our breath wondering what other impossibilities are still waiting for us, hidden in the unforgiving glare of a billion distant suns. And so, the light from that impossible world filtered through its own substance and dissected across a continent of golden mirrors finally resolves into an undeniable truth. A planet made of steam. We are left suspended in the intellectual vertigo of that revelation, standing at the edge of a newly discovered cosmic cliff. For generations, our search for other worlds has been a search for the familiar, a hunt for reflections of our own solar system. We looked for terrestrial cousins and gaseous giants, planets of rock, planets of ice, planets of crushing metallic hydrogen. Our imagination, as vast as it seemed, was still anchored to the archetypes we knew. But this discovery has severed that anchor. It tells us that out there in the grand churning laboratory of the galaxy, nature's creativity far outstrips our own. This isn't just a new entry in the catalogue, a new pin on the galactic map. It is the tearing of the map itself. It is the realization that the language we have been using to describe the cosmos has been missing entire letters, entire concepts. The universe, it seems, has a much richer vocabulary than we ever imagined, and it has just spoken a word we have never heard before. The foundations of our understanding, the very pillars of planetary science, now tremble. For decades we have relied on two grand narratives to explain the birth of worlds. The first, the elegant step-by-step ballet of core accretion, describes dust gathering to pebbles, pebbles to boulders, and boulders to a planetary embryo. Only when this solid seed achieves a critical mass can it greedily pull in a thick atmosphere from the protoplanetary disk. It's a patient bottom-up process, the one that built the Earth beneath your feet and Jupiter in its majesty. The second narrative, gravitational instability, is a more violent top-down affair. A vast, dense region within the swirling disk of gas and dust collapses under its own weight, a star-like birth on a planetary scale. It forms a giant world in a cosmic blink, bypassing the slow, methodical construction of a core. Both of these models, for all their differences, have one thing in common. They are built around the necessity of a gravitational anchor. A solid core to begin the process, or a massive clump of hydrogen and helium to trigger a collapse. But where does a world of pure water vapour fit into this architecture? How can such a planet exist without a significant rocky or icy heart to bind it? A ghost cannot build a house. The core accretion model falters here, for where is the foundational seed in a world born of steam? Did a massive ice giant form in the cold outer reaches of its system, and then through some catastrophic migration, fly so perilously close to its star that its entire solid body sublimated away? Was it boiled from the inside out, leaving behind only its atmospheric soul? Or does the gravitational instability model have a hidden chapter? We never read one that allows for clumps of lighter volatile materials to collapse under very specific, previously unimagined conditions. Perhaps the rules change in environments richer in oxygen than our own solar system, where water is not a trace contaminant but a primary building material. The elegant theories that have served us so well have suddenly become incomplete. They are like a detailed guide to building ships that has just been presented with a vessel made of solidified light. The object is there. We see it. We have measured its essence. Now we are faced with the profound, humbling task of working backward from the impossible, of rewriting the physics of creation to accommodate the creature it has already made. This moment of stunning clarity was not born in a vacuum. It is the culmination of a human journey, a testament to our relentless species-defining curiosity. It began as great discoveries often do not with a bang but with a whisper. A few lone voices in theoretical astrophysics, running simulations on supercomputers, pushing the boundaries of known physics just to see what would happen. They would publish papers often relegated to the esoteric corners of their field papers that posed a tantalizing question. What if a world could form without the prerequisites we hold so dear? These were mathematical phantoms, computational ghosts haunting the edges of possibility. For a time that is all they were. Then our first generation of exoplanet hunting telescopes, Kepler and Spitzer, began to send back their own whispers from the darkness. They would find planets of such low density that they confounded classification. They were too light to be conventional gas giants, yet too large to be rocky super-Earths. They were puffy, oddballs, anomalies that were noted catalogued but ultimately left unexplained, their true nature shrouded by the limitations of our instruments. The data was tantalizingly incomplete, a fuzzy photograph of a spectacular truth. We needed a new eye in the sky, an instrument with the power and precision to perform an autopsy on starlight itself. We needed a telescope that could catch the faint, filtered glimmer of a star shining through a planet's atmosphere hundreds of light years away and decode the chemical fingerprints hidden within. We built the James Webb Space Telescope. We folded it, like celestial origami, launched it 1,000,000 miles from Earth and pointed its vast golden gaze toward these enigmatic worlds. And the moment the first spectra came back from this particular target, a wave of disbelief and exhilaration rippled through the scientific community. The signal was not subtle. It was not ambiguous. It was an overwhelming screaming chorus of water. The absorption lines in the starlight were so deep, so broad, they painted a portrait not of an atmosphere containing water, but an atmosphere that was water. The long-theorized phantom had stepped out of the equations and into reality. The whisper had become a deafening roar, confirming a new class of planet, and in the same breath validating decades of patient, persistent, and often unheralded scientific labour. We now find ourselves in the humbling position of needing to redefine a word we thought we understood: planet. For all of human history, that word has been bound to our own experience. From the wandering lights in our ancient skies to the family of worlds in our solar system, a planet was either a ball of rock you could stand on or a colossal sphere of gas. They were variations on a theme members of a celestial family we knew intimately. Our taxonomy was simple, our categories neat. We had terrestrials, gas giants, and ice giants. But this water vapour world is something else entirely. It represents a new phylum in the zoology of the cosmos. It is as different from Jupiter as a fungus is from a lion. It forces us to ask, what other fundamental states of planetary existence are we blind to? If a world can be made of steam, could another be a crystalline sphere of diamond born from a carbon-rich nebula? Could there be planets with metallic atmospheres raining molten iron through skies of vaporized rock? Are there worlds where the line between atmosphere and ocean blurs into a single, seamless, supercritical fluid, a planet without a surface? The discovery shatters the cage of our Earth-centric assumptions and opens a door into a vast unlit room of possibilities. And with this expansion of physical possibility comes a radical expansion of biological possibility. We have long equated the search for life with the search for liquid water on a rocky surface. The habitable zone has been our sacred ground, a narrow band of cosmic real estate, where conditions are just right. But this world of steam, while likely too hot for life as we know it, challenges the very premise of that search. It demonstrates that water, the key ingredient for life, can exist in planetary quantities, in states we had not considered. Could life exist not on a planet's surface, but within its very atmosphere? Could there be extremophils, airborne ecosystems thriving in the swirling temperate layers of a world made entirely of vapour? By finding a planet in a state we deemed impossible, we are forced to reconsider what forms of life might thrive in environments we have long dismissed as uninhabitable. The universe has just shown us one of its wild cards, and it makes you wonder how many more it has in its deck. This is the legacy of the James Webb Space Telescope. It is not merely an observatory. It is an engine of paradigm shifts, a machine built to deliver awe. Its work on this single world is a preview of the revolutions to come. Every observation it makes, every photon it gathers adds a new brushstroke to our portrait of the universe, often in a colour we did not know existed. The mission ahead is clear. Webb will turn its golden eye to other puffy planets, those long-standing anomalies in our catalogues, to see if this water vapour world is a singular freak of nature, or the first known member of a vast and common class. It will probe their atmospheres for other chemical constituents, searching for the telltale signs of how such bizarre objects could have formed and survived. It will begin the monumental task of filling in the new, expanded, periodic table of planets, a chart that now includes a column for worlds made of pure vapor. Each new discovery will not be an end but a beginning, a fresh question posed to the cosmos. For every mystery solved, a dozen deeper, more perplexing ones will undoubtedly emerge from the data. We are living in the first days of a new era of cosmic exploration. We are like ancient mariners who had only ever known rivers and lakes and have just crested a hill to see the true, terrifying and magnificent expanse of the ocean for the first time. The journey from here will be long, and the destinations are unknown. There will be new worlds that defy our models, new physics that challenge our understanding, and new discoveries that reshape our place in the universe. The water vapor planet is not just a scientific curiosity, it is a profound lesson in humility. It is a reminder that the cosmos is under no obligation to conform to our expectations. It is wilder, stranger, and more magnificent than we have dared to imagine. And as you look up into the night sky, know that it is no longer just a collection of familiar, predictable points of light. It is a sea of infinite possibility filled with unseen monsters, unimagined jewels, and wonders we do not yet have the words to describe. And our journey to understand them has only just begun.